hope that you people could see this. Yeah, so in case if you have any doubts, you can come to the chat so that I can try to check the chat frequently, and then I'll try to address your questions. Okay. Yeah. So we have basically the small signal model is being drawn here, and whatever I've marked with pink color is all the internal components of this mask transistor. Now, for this, let us try to write the KCL across two different nodes. One is across the gate, the other one is across the drain. Okay, so let me write that as KCL at the gate node. And since because there are current flows through the device, like through this particular node, I will mark them. So we have one current flow from the gate towards the input through the resistance RS, the other one through the capacitance, the other one is again through the capacitance CGD. Okay, so we have three current components across this node, and let me write the KCL of it, which is written as VG minus Vin, just because the current is leaving away from the gate, and divided by the resistance will give us the current component of 1. And in order to write the second current component, I have to multiply the gate potential with respect to the impedance posed by this capacitor, and we know that the impedance is nothing but 1 by SCGS. That is the impedance posed by this gate capacitor, which I write it over here. And again, there is a current flow between the gate and the drain through the capacitance CGD. So due to which I have to first write the potential drop, or the potential difference across the gate and the drain, which is Vg minus Vout, okay, divided by the impedance posed by the capacitor CGD, which is written as S times CGD. So all of these currents would then add up to a value of 0. So that is how I can bring down this KCL. And similarly, I can write the KCL across the drain as summation of 4 different current components. One is the current leaving out this drain terminal through the gate capacitance CGD, and one is the voltage control current source, and again through a capacitor CDS, and the fourth current component is the current that flows through the drain resistance RD. So we basically have 3 current components that are leaving away from the drain terminal, and due to which I'll just quickly write down the expression, which is Vout minus Vg into the impedance posed by the CGD plus the voltage controlled current source component GM-VGS, and the current flow through the capacitor CDS, and we have the current flow through the drain resistance RD. So again, all of these components will add up to have a current value of 0. Right. So basically, from this expression B, I'm just going to evaluate the gate term. Okay, so which when you try to do some simple algebra, you would end up having something like V out into S CGD plus CDS RD divided by GM SCGD. Okay, yeah. So there was one comment from Saurabh. He couldn't able to see. Maybe I guess you have to check with the internet connection. I'm believing. But how about others? Can you able to see this? if you have the same issue with everyone, then I can check on my end. You can actually directly comment. Okay. Yeah. So Bhargav says to increase the video quality to 480p or 720p. So Saurabh, you can do that same. Uh, I guess it will be clear when you visualize in these higher resolutions. So I'll just continue my session. Okay. So basically, I'm going to derive this gate potential in terms of V out and V in, such that this Vg expression has been coming out of our B expression, and I would mark this as my expression number C. Now I'm going to substitute this expression C onto this expression A, and I will write only the final expression of it, which is V out by Vn of S, and that will have something like S times CGT minus GM into RD divided by RD RS and a factor eta. Okay. So I'll just talk about this eta, but before I do this, let me completely write this expansion. And yeah, so I guess it would be clear if I could talk about it right now. So basically, let us assume that we have two poles in a system. So we know that each of these poles could be written as, so let me write only the denominator polynomial having two poles in a system, which I write it as omega p1 plus 1. This is the first pole, and the denominator polynomial, including the second pole, will look something like this, right? And after doing this simple algebra, we would end up having something like s squared divided by omega p1 into omega p2. And then we have one more coefficient associated with an s term, okay? And then there is a 1. So clearly you could be able to see that whenever we have uh, an s squared term, the s squared term should have two poles in it. Okay, so as like omega p1 and omega p2, and each of these terms will have a simple quantity like 1 by rc. So let me write it as 1 by rc1, and so this one would be like omega p2 will have something like 1 by r2c2. Now in general, the coefficient of this s square will have some sort of terms which is a combination of this r1 as well as r2, and again we have c1 and c2, so c1 into c2. So this is how we wanted this s squared term. Okay, and when it comes to this coefficient of this s term, you could be able to see that it is again a combination of rc, so which would be like something like this. Okay, so c2, and this is what we would expect for a coefficient of an s term for the denominator polynomial d of s. Okay? Yeah. So now what I really wanted here to see is that you can able to see that there are two resistances Rd and Rs in the place of R1 and R2 that I spoke before. But in the place of C1 and C2, I've replaced with an extra term which is defined as eta. Now, what could be this eta? Now, you could see that there are not just two capacitors, but we have three capacitors here. Okay, CGS, CGD, as well as CDS. Now, each of these three capacitance has to be combined as a combination of two at a time. Okay, so due to which each of these capacitors will actually share with the other capacitance as a two capacitors at a time. And based on this, one could write the factor of eta to be equal to CGS with CGD and CGS with CDS. And again, what is left over, one of the combination that is left over is the combination between this CGD and CDS. Okay, so hope that you're clear. So what we wanted is been satisfied here for an S square coefficient, we need a combination of R1 and R2 along with C1 and C2. So in this case, the C1 and C2 would be a term over here, and C1 and C2 would be a term like this. And just because we have three capacitors, we need to step down to two capacitors with this sort of combination. So why I'm trying to emphasize here is that this will help you to recollect the final expression and see whether you're ending up to this final expression after doing all this simplification. Okay. So basically, this would be asked for sometimes around for 10 marks. So after doing all these steps, like I've basically skipped many of the intermediate steps, but in order to gain the whole mark, you have to further do a few more steps in order to get down to this final expression. Okay, but ensure that the expression for A, B, and C are all written, and then you write few more steps in between before you write down this final expression of V out by V in of S. Okay, yeah. So hope that you're clear with this. So I'll just continue with this, and I'll write down the complete expression of the denominator polynomial D of S. So again, we have a resistance Rs, and that has to be combined with only one single capacitance. And let me take the first capacitance, which is GMRD times that of CDS. So this is one combination of R and C. And there is one more combination of R and C, which is RS with CGS. And we also have one more combination just because there is a second resistance, and that resistance will get combined with CGT and CDS. Okay. Now, as you could see, each of the terms here is always a combination of R as well as a C. Okay. So ensure that you have the coefficients of S term exactly replicating just a single R and single C component in it. Okay. And along with it, add just one. Okay. So this is what we have. Now, as you could see that when I try to uh, look at this particular polynomial that I've written down here, it's pretty sure that it's a second order polynomial. And it also ensures that we will have two poles in our system. And if at all, if I assume that these two poles are just omega p1 and omega p2, then we need to extract these expressions out of this coupled second order polynomial, right? Yeah, so we need to strip down the value of omega p1 and omega p2 out of this coupled equation here. Right? So the way by which I can uncouple this expression and strip down the value of omega p1 and omega p2 is having some sort of assumption. Okay, so let us assume that I have omega p1 being the lowest frequency than compared to the omega p2 term. Okay, now under this approximation, just an approximation. So under this approximation, one would have this d of s polynomial as something like omega p1 into omega p2 plus, since because the value of omega p1 is much smaller than the value of omega p2, this omega p2 would then be driven to 0, just because anything that is divided by a very large quantity would then step down to a very small value. Okay, and due to which I would approximate the quantity of 1 by omega p2 to a value that is equal to 0. And because of this approximation, I'll have an S term that has only a pole frequency of omega p1. Okay, and then with 1. So now it is just a straightforward way, just by comparing this polynomial that I returned for v out by v in of s with respect to d of s, right? So the value of this omega p1 could be written down directly by looking at this expression. Okay, so I have this omega p1, which is defined as 1 upon the whole expression that we have written down for the s coefficient Okay, yeah. And now that I just want to strip out the value of omega p2, And that could be done just by looking at this particular S square polynomial, which we know it has two poles in that particular coefficient. Okay, so now that I'm just going to compare this expression, okay, with this coefficient of this S square, so which would be something like I have this omega p1, omega p2, which is 1 upon this term, supposed to be equal to Rd, Rs, and the factor of eta. Okay, so just by comparing the S square coefficients. So from here, I could write this omega p2 as, I think, as 1 by omega p1 into 1 by Rd, Rs, and then the factor eta here. Okay, so again, substituting back this omega p1 value here, you would have Rs. It's a whole lengthy expression, but I'll just write down only the final expression of it. Divided by this Rd, Rs combination along with the total combination of CGS and CGDs. So CGS with CDS and then CGD with CDS. Right. Yeah. So this is what I have for the expression of omega p2. Now, as you get able to see that this expression is completely different from what we have got when we use this Miller's method, right? So in the case of a Miller's method, we wrote down the value of omega g as something like, I guess, it is equal to 1 by Rs into CGD into 1 plus GM RD plus CGS. Okay, and this was the pole frequency that we evaluated at the gate when we use Miller's method. But the same, when I look here, which is nothing but the omega p1 in this case, we still have the same expression of Rs into 1 plus GM RD into CGD along with CGS. But there is an extra term that gets added up when we really compute the real transfer function. Okay, so that is what I said. The Miller approximation or the Miller method will give us only a rough estimation of the pole, but the exact pole have to have these expression added to it. And again, let us try to map the omega d value. So again, the value of omega d is written as Rs into CDS plus CGT, and that was the pole that we have estimated in the case of a Miller's method. But when I look here, it's completely different. Okay, there are a lot of terms that is involved here. So that's the reason why I stated that the Miller's method doesn't estimate an accurate pole frequencies. But I also stated one more thing, that they not only gives us an inaccurate pole, but it doesn't show up any zeros. But let us look where our zero exists. As you could able to clearly see that there exists a zero out of this expression that could be extracted from here. Now let me try to pull out the quantity of GM out of this numerator polynomial. Okay, so let me write this numerator polynomial as n of s, and which is defined as GM. Sorry, it is defined as S CGD minus GM, and the whole of this thing is being multiplied with RD. And let me try to pull out this term GM away from this numerator. So I guess one would end up something like and with a negative value of minus GM RD. Okay, and this particular quantity right now gives us the zero component out of it. Okay, but there is something fishy about this zero term. As you could be able to see that whenever we write the pole, we always had something like omega p1 or whatever it is. Okay, so any pole always had a plus signature associated with it. But when I look here, this particular zero has a negative sign attached to it. Okay, so this means that when I try to plot this zero frequency in an S plane, this zero frequency will appear on the right half of the S plane. Okay, so we'll have a deep discussion about it. Probably I will share this video about stability after this, but we'll discuss about the complications that are introduced by this zero towards the right half of the S plane. Okay, so as of now, the one thing that we need to observe here is that this results in a right half zero frequency, whereas all the poles that we have computed will all fall in the left hand side of the S planes. Okay, so that's the only thing that I want to emphasize here. Okay, so any doubt you can post it uh, in the chat. Otherwise, I'll keep continuing this lecture. Okay, so let me try to finish this by plotting all this transfer function that we have got. And again, I'm just going to write it as small letter a in order to denote the transfer function gain. And I will plot only the magnitude plot of it with respect to the logarithmic scale of the frequency. And clearly from here, one could roughly say that the value of omega p1 to be the lowest frequency. And after then, omega p2 will appear, and then omega z. Okay, so I'll just mark those pole frequencies here, and then omega z. Now, as said earlier, each of these poles, I could roughly draw a linear approximation for the magnitude plot. Okay, so there will be a degradation of gain by a rate of minus 20 dB per decade, and when we meet the second pole, then this will further decay the gain by minus 40 dB per decade. Okay, so probably this will be much more flatter than compared to this. Yeah. So when we meet this zero, we know that zero term will generally add plus 20 dB per decade rather uh, minus 20 dB per decade, right? So due to which, what happens is that the gain will again steps down at a different rate, which is minus 20 dB per decade because of this zero. Okay, so in short, zero will add plus 20 dB per decade, whereas a pole will add minus 20 dB per decade to the transfer function. Okay, so with this, let me stop here. I'll just have to discuss about few more things related to this frequency response, which I will do that in the next class. And after that class, I will also share the link. Probably today only I will share the links. You can just watch those links after this complete discussion of CS amplifier. Okay. Yeah. Thanks for listening.